So let's go ahead and draw these out. This is a double convex lens, and we're going to do this following the same basic rules, but we're going to use refraction instead of reflection. So what was rule number 1 for mirrors?
Draw parallel.
Okay, so we're going to do that again. So we're going to draw a parallel line. Now notice in reality what's happening. How many points of refraction is occurring? 2 points, right? When it goes into the lens and when it leaves the lens. However, we're just going to refract it once at the very center just for simplicity. So we're going to refract it once at the very center. So go ahead and draw that beam 1. This is going to be parallel. Again, we're using the tip of the object there. Draw it to the center vertical. Okay, so draw it to the center vertical. And what's the second part of this rule? It's going to refract. Now remember with mirrors, how did it refract? Through the focal point. We're going to do the same thing. However, it's refracting, so it's going through. It's not reflecting. So we're going to refract it through the opposite focal. So you're going to take your ruler, you're going to line it up with the focal on the opposite side, and send the beam on through. Okay, rule number 2. What was rule number 2 before? Through the focal, and then what? And then it goes parallel. So we're going to follow that same basic rule. We're going to draw a line. Now we're going to draw, there's 2 focals. Which focal do you think we're going to draw it through? The first one. So we're going to draw it through the same side focal point, and then we're going to refract the beam parallel.
And it's refract at the center?
It's always going to be with the center, yeah. So in reality it refracts twice. And you could do that if you wanted to. You'd have to just use some Snell's law and crack out a protractor. It's a little bit easier to do it this way. So that's the way we're going to do it. And then we're going to send it parallel. Right, then we're going to do beam 3. What was beam 3 before? Through the center of curvature. Now this rule is going to be different than that, although the language we'll use will be very similar. What we're going to do is we're going to draw a line through the center of the actual lens. Okay, so we're going to draw a line through the actual center of the lens. So what you do is you take your ruler, you're going to aim it here with the very center of the lens. And this is what's going to happen. When this beam hits the lens, it's going to hit it right on the normal. It's going to hit it right on the normal. So what should happen if it hits right on the normal? Doesn't refract at all. It just keeps moving in a straight line. And so that's what you're going to do. You're just going to keep the line going straight through. Okay, so we'll just write no refraction happens. So in other words, we're just going to draw our line straight on through the lens to the other side. And if you draw correctly, you should have a nice three-way intersection. Okay, right here. That represents the tip of the arrow. So go ahead and finish up your arrow, draw on the rest of the arrow. Okay, there's your image. So why don't you let's measure out our image distances and our image heights. Getting a DI of about 4.9. Right, hopefully you're in that ballpark, 4.8, 4.7, 5.0. Let's measure an HI. Getting an HI of about 1.2, it looks like. Now this is an upside down image, so what should I do with my HI?
Negative.
It's going to be negative. Okay. So just like with mirrors, there is an equation. There are two equations that govern the math of this. And luckily for us, the equations are identical. So we'll call this the lens equation. 1 over f equals 1 over di plus 1 over do. It's the exact same equation. Okay? It's nice how physics does that, doesn't it? Just works. 1 over f equals 1 over di plus 1 over do. So let's see what we should have gotten. If you drew this perfect, what should you have gotten? So do the math for me. What's our theoretical DI? 4.8. Okay, so that was pretty close. Anyone actually get 4.8 in their measurement? A couple of you. Let's see what our HI should be. So the magnification equation is the same. HIHO, negative DIDO. I do want you to notice that we did get a positive number for DI. This is one of the differences between lenses and mirrors. A positive image distance tells us where's the location. On the opposite side. With mirrors, what was a positive image distance? On the same side. Okay. One of the ways maybe to remember this is think about what should light do. So light should go through a lens and end up on the opposite side. That's positive. Light should reflect off a mirror, end up on the same side. That's positive. So whichever the positive number is, that's what light should be doing. Lens versus mirror. Okay, let's find out what our HI should be. HI over HO. My HO is 2. My DI was 4.8. And my DO was 8. Okay, so it looks like that's 1.2, isn't it? Did I do that right? Negative. And so what's the meaning of the negative?
Inverted.
Inverted. So that's the same as before. It's inverted. You can see that's what happened. Lastly, let's get the magnification. hi over ho. So we got negative 1.2 divided by 2. And once again, we have a negative. That means inverted. And what's the meaning of the 0.6? Smaller. Okay, and our image is smaller. Last question. What do you guys think? Is this a real image or a virtual image?
Real.
This is real. Again, the reason you know is that light is actually converging at a point. All this light is coming together. It's converging at this single point right here. And so you would see an image. This would show up on the screen. And actually what you're looking at right now is a real image. So this is a real image on the screen. We're projecting my paper here through the projector, and there's a lens there, a convex lens, and then we're getting it on the screen. Therefore, this image should be inverted. So if I move my pen to the right, that way, what should happen when you look at it on the screen? Okay, goes the opposite way, right? So our image is inverted. It's being inverted as it comes through.